Thank you for your attention. So, Tim Hagen from the Erasmus Medical Center. I have nothing to disclose. Whether you have fancy old fancy stuff like the checkpoint inhibitors, or you have old drugs, you need to get it to the tumor. And if you look at a molecule like an antibody, or you look at chemotherapeutics, what you actually get is that you have nothing in the tumor and you have everything around in the body. So the question which I ask often to students, but also to people who are already a medical oncologist, is how much does it get to the tumor? They dare to say 10, 20, 30, even 50%. It's not. It's 0.01. In antibodies, it's 1 out of 100,000. So of all these pembrolizumabs and ipilimumab, and I don't know what type of maps, nothing gets into the tumor. So we need to work on that, because what you have is you cannot just give 100,000-fold more. You will kill your patient. So the major impact on therapy is that you have poor outcome, but the most insidious effect actually is the side effects and the morbidity. And they prevent you from having an effective therapy. So you need to do something else than dosing higher. So what do you do when you have a patient like this? This is a recurrence. There was a melanoma primary taken out. Then you have satellite, you have recurrence, and you have intransit melanomas. What do you do? So the option this patient got, a Swiss lady, was amputation just below the knee. That is one thing you can do. But she got a treatment which resulted in this, a total cure. And out of all the patients which came in and got that type of treatment, 100% of the melanoma had local control until they died of distant metastasis. Of the sarcomas with this, I have the next picture. Of the sarcomas it was like 75. So why is that? That is because of this reason. These patients get an isolated lymphofusion. What is that? Isolated lymphofusion is that you only treat that part of the body which has the tumor. What is the effect? The effect is that you decrease the volume over which the drug can distribute. It cannot get out, and you can give it only to this area. So volume shrinkage, which is for, like doxorubicin, is thousands of liters, is now suddenly a couple of liters. So that's the first one. So if you have a sarcoma patient like this, normally you can, of course, surgically take it out, but I can assure you it's not looking nice. This person got an isolated lymphofusion and had a full response and walked away with his leg. So we want to do that also for the body. We want to limit the volume of distribution from thousands of liters to maybe 4 or 5 liters, so it stays in the blood, and then you want it to get into the tumor. You want to get higher than this really devastating 0.001%. So you have the free drug. What is the main reason it goes everywhere is it's cleared fast. Clearance is fast, and it spreads out over the body. So first there were people who made carriers. We used liposomes made of phospholipids. I'm not going into detail, but one thing they did, what was the most important, was extending time in the blood, residence time, from a couple of minutes, also most people don't know, to, in patients, like 3 days, half time. So there's more chance of this drug to get in the tumor. So Bette Gabizon and Jechel Barholz, who were instrumental to making Doxil, Calyx, showed that in one of their papers, where you have in patients, independent of dose, you have a really nice kinetics of Doxil compared to the free compound. But one thing is that total and encapsulated were the same over the whole time. So while it was a really nice compound to give to patients to have a longer residence time in the blood and don't have this fast clearance, it stayed there and it stayed together. That's a problem, and we showed that in this paper from cancer research. We showed that these liposomes made green, and the doxorubicin is red, that these liposomes would end up to 3 days later in the cell, in the cytoplasm. They were sitting there, and not giving away their drug. The thing is that Doxil, Calyx, is not registered for being more active. it's registered for being less toxic than the free doxorubicin. And this is the main reason. It's sitting there and it doesn't release the drug. It cannot go to the nucleus. So we need to do something about it. So here you have Doxil. It's 100 nanometers, so quite enlarged, so you can see it, with doxorubicin inside. And what we would like to do is give it a pulse, and then the drug comes out. That would be really nice. So one of the ideas, and that we made a liposome. Other people made a liposome. There's also Tumor, where if you start to heat at 42 degrees Celsius, within a fraction of a second, most, if not all, of the drug is released. So now you have a liposome, like Doxil, which circulate long, but it has an addition that is that it's responsive to a slight change in temperature, which we can achieve in a human setting. And then when you reach that, you can release that. So the idea is then to have this liposome circulates nicely long. It enters from here into the tumor area, and as soon as in the tumor area, that area is heated, so that is actually the thing which is the focus, which determines the targeting of the tumor. As soon as it comes into that heated area, it releases the drug, and the free drug will go out into the tumor. Intravascular triggered drug release. This is a liposome working like that. The liposome has doxorubicin in it, so you can see it fluorescently. As soon as we heat it up, it will go out and you see more fluorescence. It's de-auto-quenched. And you will see vessels in the mouse which are green. This is in collaboration with Lars Lindner, who made these liposomes really nicely, and they're very effective and very fast responding to hypothermia. So here you see the vasculature being green. The drug is coming in. We start to heat up slowly to 42 degrees Celsius, and as soon as we hit above 41, you will see that the drug comes out and distributes nicely. So that is a new step. So that is now the drug is out in the tumor only, and not in the not heated, or I would say in the heated zones only, and not in not heated, preferably if it is tumor. And you can see it accumulating in those cells. And this is, I can assure you, you can give 30-fold more of this drug, and you won't see it in this setting with the same gains and settings. Okay. But there is another thing. So this was analyzed by Dieter Heimerich at MUSC, and he showed that we were able to get the drug over time, and these time frames. We got the drug in there while we were heating, then we switched off the heating. We had a nice deep penetration of over 100, but then as soon as we switched off the heat, it started to go down again. You started to lose drug again to the system, because if the liposomes are not heated, they're closed off, so you have a negative gradient back to the vessels. So what you get is liposomes come in, release the drug really fast. Most of them have it released, so you have a big flush in, but you also have a big flush out. And this, of course, we wanted to make smaller. What is happening? What's happening is that we deliver so much doxorubicin in such a short time frame that not the amount is the limiting factor, it's the capacity of the cells to take it up. Now suddenly doxorubicin is not an ideal drug anymore because it's taken up really slowly by the cells actually. So we look for another drug. So you have doxorubicin, which is registered for systemic use for a lot of cancers, it's Doxil. And you have idarubicin, has a single registration only for hematologic cancers. Why? Because it circulates even shorter, but it's taken up by cells really fast, so it will never ever reach a tumor. So it will never ever be registered for solid cancer treatment. But we put that in a liposome. And we see that if you give it to cells, it's a rationale because it's taken up by cells so fast, already in the first minutes, seconds, while doxorubicin takes a while. This is in vitro, eh? Vitro cells uptake over so many hours. So this is really picked up fast. Thermosense liposomes together with heat is actually a local therapy. So you should not use a drug which is systemically applied, but you should use idarubicin. So here you have the same thing. You have green vessels, and now we infuse idarubicin liposomes. Hope it will run. Oh. I am doing something wrong, I guess. I still got 2 minutes. So. There it comes. So now you see it getting out, and you see that it really gets stuck around the vessels. So it gets out, and it's picked up really fast. And when we get to the end, you also see no drop in the amount which is delivered. Hardly. But being not fooled, you think there is nothing here, but that's a matter of the gain settings. When we analyze this, then we have here idarubicin, and here on the same scale doxorubicin. So idarubicin is taken up really fast and sticks there at a really high level, while doxorubicin is hardly taken up because it just goes there, sits there, and then is flushed out. Only when we make the scale 10-fold different, or 100-fold different, then we see that doxorubicin has the same profile, only not that sharp. So idarubicin is actually a much better drug to do that. So if we use that in a mouse model and look at efficacy, then, and we have to compare that with a clinical doxil dosing, which is many folds more than the dose of single dose of idarubicin. This is 3 times over this period here. Then you see that only idarubicin thermostatic liposomes together with heat gives you tumor control as you want it. So to wrap up, is like if we want to move forward with this type of thermostatic liposomes and delivery of that, we need to look at it as a local therapy and use other drugs than doxorubicin. So I want to thank people in the lab, especially Tao, who's going to get his thesis defense in June. And I want to thank these people here for helping me doing this research. And thank you for listening.
Thank you. We have time for 1 or 2 quick questions. There's one there.
Thanks. What do you think of the organotropy of chemotherapies? I mean, doxorubicin is not necessarily good for every cancer.
Oh, I totally disagree with that. I couldn't disagree with that more. I think that is such a nonsense. I mean, that comes all from really old things and how the tumor is built and everything. If you have a hammer and there's a mosquito, it doesn't matter how big the hammer is. If you get it, you will kill it. So we test doxorubicin on many cells. And yes, indeed, you have different toxicity profiles. But you're looking now at a 30 to 100-fold more delivery of the drug in that setting. If you can get that all to stay there, I can assure you can kill a lot of cancers. And the main thing that sometimes cancers are not responding is because of their acquired resistance. Well, you have indeed sarcomas which are 100 to 1,000-fold more resistant. If we can improve this, we also see that IDA is more effective to that type of tumors than doxorubicin, then you can deal with that. So we think you have to think out of that really classic, poured in concrete type of thinking and move towards a drug which is really good in that setting. And that's the same for the isolated lymphofusion. We use, for instance, in Rotterdam, melphalan for the isolated lymphofusion. While in Italy, they use doxorubicin because they are sarcomas. What works better? Melphalan. It flies into the tumor. It is so fast, it sees no boundaries almost. So you have, within the perfusion time, you lose everything inside that part you perfuse. You use doxorubicin, it's too slow. So you have to start thinking different. And I agree that tumors will have resistance or will have some resistance, but if you go beyond that level, the toxicity level, you will kill a lot, okay?
Okay, thank you. Very interesting.